everyone. Welcome to this lesson. And my name is Raffella Boggia. I am a food chemist, and with my research group, we are working in the Department of Pharmacy at the University of Genoa. The topic of this lesson is the sustainable food ingredients and the so-called nutraceuticals coming or potentially coming from food side streams. With these terms, we intended as the biomasses which are unavoidable residual outputs that usually remain unused and which usually have to be disposed of at high cost. On this slide, you can see the outline of this lesson. First, I would like to briefly talk about the context of this topic, trying to answer the question why we care on this topic. As second, I would like to introduce the concept of upcycling food, which means taking leftovers and converting them to produce alternative or novel ingredients with high added values, what is also referred in papers and in some scientific documents as bioproducts to value products. Trying, in this case, in this second case, to answer the question, what are we talking about? In the last part of the lesson, we will try to provide you some case studies. And Federica Turrini, my colleague, will introduce you a lot of case studies we have investigated in our lab. In particular, a special focus will be made on fishery side streams, as we are actively participating in the research activities of EcoeFISHent project. So let me start with the context, with the background of this lesson, and speaking about what probably all of you well known, that growing global population is expecting to reach about 10 billion by 2050, resulting in the search for a healthy lifestyle and appropriate meals to retain good health, as well as resulting in increasing demand for a nutritious and sustainable food supply. With less than a few years left to reach the Sustainable Development Goals, much still must be done to improve the way we produce and consume food. We have to work to achieve global commitments, making our food system able to safeguard our health and the ecosystem by delivering affordable diets to everyone, everywhere, and possible at all times. In line with this approach, the double health and climate pyramid has been developed as a guideline for daily food choices that are healthy for humans and more sustainable for the planet, showing that the food we should consume more frequently for our health are generally also the ones with a low climate impact. On the contrary, the production of animal foodstuffs and factory farming are associated with major negative impacts on the environment and the human health. These reasons lead to the search for sustainable food alternatives by focusing on the preservation of wasted nutrients within the food chain, paying particular attention to proteins, and always respecting the principle of sustainable circular economy. In other words, the efforts we will have to make are aimed at achieving what is generally summarized with the concept of One Health, an integrated, unifying approach to balance and optimize the health of people, animals, and the environment. So we can, easily understand as one of the main challenges is proper the development of a sustainable solution for the management of a food industry side streams. In fact, it is estimated that roughly 1/3 of the edible parts of food produced for human consumption get lost or wasted globally. corresponding to about 1.6 billion tons per year, involving byproducts such as bagasse, peels, stems, shells, seeds, bones, skin, scales, and so on, as well as whole preparations threshed for not meeting the commercialization quality criteria, ripeness, size, color, odor, etc. All these biomasses need to be managed and disposed with a loss of about 2 trillion euros, and this data is expecting to increase within next years. However, if correctly managed, several nutrients and bioactive compounds can be still extracted from different food industrial side streams, turning them into high added value products, drastically reduce social, economic, and environmental impacts due to their disposal or incineration. Indeed, food side streams minimization, together with the possibility of bioactives recovery and their modification through green methodologies, can represent an attractive opportunity, not only for the development of new food ingredients, but also for nutraceutical, cosmetic, textile, and pharmaceutical sectors, among others. So it is, mandatory to manage food side streams. In my lesson and in the slides that I am showing you, sometimes you will find this kind of sign, the attention sign, because when the sign, will appear, is just to remind you that it's quite important to develop and possible to study and to investigate this topic, because they are sort of hot topics. So another question is where are food side streams generated? Because you know that we can, in a certain way, try to, schematize the food chain and in different steps. And so this is an example, and it's quite a general example. And production, storage, processing, distribution, retail, food service, consumption is typical steps of a typical food supply chain. In the first steps of this scheme, usually the 30% of food is wasted. The others about the 60%. So many strategies can or could be applied from improving the efficiency of all these steps to the recovery of food, in example for charity, feeding, composting, and so on. So the topic of this lesson is about the valorization of these food side streams, possibly not only recycling them, but adding value to them, the so-called upcycling, making food side streams a new resource for food sectors, but also, as I said before, for other sectors. Now, I would like to, explain what is the, example we are talking about in the context of EcoeFISHent project, and in particular, what is a fishery side streams. Because, I would like to give an example of what we manage every day in our laboratory. And precisely about, in this case, we are talking about two different types of fishery side streams. The first one that you can see in this part of the slides concerns about wolfish coming from, example, unwanted catches, bycatches, or undersized catches. As you know, when you are fishing, you can catch also something that you don't want, or something that consumers don't want. because the size, because the kind of fish is not what we are expecting to. The second kind of fishery side stream is different and is typical of, for example, industry, which is involved in preparation of some fishery products. For example, an industry which is involved in the canning process. For example, canned tuna as a typical product, or for example, filleting to produce fish fillets in order to prepare a ready to consume food to distribute in supermarkets or in the shops. So we have two different kinds of fishery side streams, but in any case, we have a very peculiar biomasses, because this kind of biomasses is very, very perishable. This is because, as you can see, this solid fish waste is a very heterogeneous biomass, that it is potentially dangerous if untreated in fish farms and post-harvest systems. The fish leftovers, such as bones, head, skin, scales, fin, tails, gut, and viscera, occur in variable proportion according to the kind of fish and the kind of process. Given that these fractions rich in organic content are dumped in landfills, environmental threats associated with land and water contamination become a matter of concern. With its nutrient-dense composition, improper handling and storage practices can rapidly deteriorate fish quality, making them unfit both for consumption, but both for further processes like upcycling. This includes their exposure to unacceptable duration of high temperature, poor infrastructure, and the reliance on certain traditional post-harvest fish processing methods that are associated with high levels of wastage and environmentally unsustainable. Thus, recovering valuable components before disposal become the prime target in solid waste management. However, even though fishery side streams represent a valuable resource consisting of many high-value components, such as bioactive peptides, collagen, chitin, or enzymes, we speak about them in a few minutes, it commonly uses to produce fish meals, fertilizers, and fish oils, or serves as direct feed in aquaculture. One of the bottlenecks in the flow chart to valorize them is their sorting, and for this reason, many efforts in EcoeFISHent project are devoted to use unsorted biomasses. But in any case, it is mandatory to block degradation and spoilage using a stabilization step. As I mentioned before, this is a very perishable material. In this next slide, you can see a general flow chart resumed in a research paper I cited here, suitable for food side streams in general, with, in this case, another special focus not on animal but on plant-based foods. In any case, many of these steps are common, and the pretreatment, which I sign with this, sort of red square or red rectangle, is quite important and has to be declined according the kind of biomasses you have to manage. So the first requirement is, according to the material, milling, grinding, or in any cases, try to block any kind of chemical or microbiological degradation. So, for example, coming back to the example of a fishery side stream, cleaning, sorting, cutting or grinding, and making something to stabilize this product. For example, the hydration, but not only. There are some, methods to stop any kind of degradation. As you can see, sorting is highlighted. It's highlighted because this is a very important step, and as I mentioned before, in EcoeFISHent project, we are trying to avoid this because this sorting is really expensive and sometimes is unaffordable for some, stakeholders. So, in scientific papers, but also in industrial processes, you can see some tables like this one, in which you can realize that if you are particularly interested in some application and in some bioactives, you have to sort and to separate the skin from muscle, from belly part, from scales, from viscera and head and skin. And as I mentioned before, this is a very heavy step. So, I think, have understood which is the background of this lesson. Please let me go to the next or the second topic. That is, to try to explain this concept of recycled food or recycled ingredients. An old concept in some way, but to be implemented in today's industrial food system. Sometimes we, forget some golden rules that probably our grandfather and grandmother tried to teach us, but the usual food system, obliged us to, to forget some golden rules. And obviously, we have to decline these golden rules in a food industrial supply chain. So, which is, what is the definition of this concept, the upcycling food or upcycled ingredients, that could be different according to different point of view. For example, for researchers, for food manufacturers, for stakeholders. So we have also to work about policy and regulation development, because otherwise much of the research carried out in this field can become feasible or not in practice. In other words, upcycled food is sometimes allowed and sometimes is not allowed yet. Then we would like to defining a sort of waste management hierarchy from most to least favorable action, and obviously the communication and public acceptability of these upcycled ingredients or foods must be investigated and must be considered, because as you can imagine, this public acceptability is the last step for this kind of products. So please let me show this next slide, in which I would like to show you an example of upcycled food. In this case, we have, an example of upcycled food constituting through alternative use. In this case, we have probably, chickpeas. And, then to cook chickpeas, you have to add water. And this water that you produce during the cooking of chickpeas, also at home, is now called aquafaba. So aquafaba is a sort of example of an alternative use of what is usually waste. In fact, when we cook chickpeas, usually we waste the water and we don't use this kind of product that we can call byproduct. But this aquafaba is quite popular for vegans. In fact, they use it to replace fat and to replace thicker agents in order to prepare some dishes and some preparations like those that are, shown in this slide. So this is, an example. And but we can have another kind of, not alternative use, but in this case, we have novel use. This is, an example of what we are speaking about before, so fishes, and what is called fishery side streams, heads, bones, and scales, viscera, and so on. And our efforts also inside the EcoeFISHent project is to try to, recover this kind of bioactives and, give them a novel use as food ingredients, as nutraceuticals. But obviously, we have another sign here, another, attention sign, because policy and regulation must be considered, because sometimes we can have a sort of novel food, and in a few minutes we will speak about this kind of definition, understanding which are the, all the possible consequences in the use of these products. So let me give you some definitions in order to be sure that everybody, is has a sort of background knowledge of this topic. So, as you know, bioactive ingredients sometimes are the ingredients that we can find in products like food supplements. What's a food supplement? Food supplements are a concentrated source of nutrients, sometimes for example, vitamins food supplements, or mineral food supplements, or protein food supplements, or other substances with a nutritional or physiological effect that are marketed in those forms. What we also called like a drug, but they are not a drug, they are food, and are, pills, tablets, capsules, liquids in measured doses. But they are, concentrated sources of nutrients or other physiological bioactive substances, but not drugs. A wide range of nutrients and other ingredients might be present in food supplements, included but not limited to vitamins, minerals, amino acids, essential fatty acid, fiber, or various plants and herbal extracts. It's important also to say that food supplements have a regulation, a European regulation, which is also, converted in in case of Italy, Italian regulation, and they are well defined. Sometimes there are another definition that is very important to know in this context, that is novel food definition. When I just mentioned novel use before, sometimes it's important to recognize that we can face novel food regulation. Because, as you know, under UE regulation, any food that was not consumed significantly prior to a particular date, that is May 1997, is considered to be a novel food. And so, it must be authorized. Otherwise, it's not possible to commercialize it. And so, even if your research is really good and your results are, outstanding, you cannot commercialize your products. Then there are another important concept that I would like to remind you. That is health claims, and in particular, health claims regulation. Sometimes we are speaking about some special foods with some, attributes that go behind the nutritional value. In this case, some foods have claims. Sometimes they are nutritional claims, low fat or high proteins, high level of vitamins. But sometimes they have a stronger, claim, something like a health claim. A statement advertising that the product has some particular health benefits. Also, in this case, you cannot say what you want. You cannot, have a label in which you can write a message that is not ruled. And so it's really important to know that also for these health claims and also for nutritional claims, you have a regulation, and so you have to respect it. And this is important because sometimes, as in this lesson, we are speaking about nutraceuticals. And nutraceuticals are ingredients, food ingredients also in this context, that have extra health benefits in addition to the basic nutritional value found in foods. So they are compounds that are able to give you some good, positive help in your healthy status, but they are not drug, but, they are not a food recognized category. So in this case, differently from these other cases, you have no rules. So in this case, a regulation is still lacking, and you can speak about concepts of nutraceuticals, but they are not defined by rules. So this is important to know. So we speak about nutraceutical, but then if we want, to use them, we have to understand which kind of targets we decided to have. For example, we have extracted nutraceuticals that are approved for their use in Europe, and so we decided to concentrate them and to produce a food supplement. Or you have a nutraceutical, but you are in this second category. And so you have to control if they are approved or not. Because if they are approved because they are old ingredients, or they are approved novel foods or novel ingredients, okay. Otherwise, you have to manage to authorize your new nutraceutical. Then you have to manage with health claim regulation, because you have to be sure that what you are, trying to assess, the bioactivity that you are trying to assess for your compounds, has an health claim which is already regulated. In this slide, then, I would like to show you some examples in which we, in our lab, have tried to extract this kind of compounds called nutraceuticals, like fibers, polyphenols, hydrolyzed peptides, omega-3 fatty acids, minerals, and so on, from food side streams, and concentrated them, for example, in order to design dietary supplements, or in order, to be added to some foods in order to prepare an enriched food, or to prepare a sort of food with claims that we also can call functional foods. Another example of compounds that can be extracted from food side streams are food additives. Food additives, are ruled. We have an European regulation that define them. I just would like to remember you that they are substances added intentionally to foodstuff to perform certain technological function, for example, to color, to sweeten, or to thicker, or to preserve, or to emulsify some foods. Also, in this case, we have to pay attention to policy and regulation. So, coming back to upcycled food, that are food that we have already defined, food with an alternative use, sort of bioproducts that we have recovered, and we have decided to recycle for alternative use or for novel use. In this case, obviously, we have to follow a sort of hierarchy. This is because food supply chain has a lot of waste, has a lot of side streams, but the first topic that we must follow is to prevent them, is not to produce a lot of these food side streams. Then the second most preferable option is to reuse surplus of food if it's possible. And so, for example, to donate them and to use them for human consumption. Otherwise, we have to think about another kind of destination, like animal feed. But if succeed in upcycle our food production, our food side streams, we can put them, in the middle of redistribution and animal feed reuse. So differently for this kind of pyramid, which is the pyramid that you can find in many government sites, in this case, not a recycle, but an upcycle. So in this case, we can upcycle some bioactives and use them just, under the redistribution step. Obviously, we have to communicate this kind of positive aspects in order to improve public acceptability. A lot of strategies can be followed, like low price, some communication on the label, and something like that. So I think that we have understand why we are speaking about this topic and what is a food, an upcycled food ingredient. And now let me go briefly in a practical example. In this case, we are speaking about fishery side streams, and fishery side streams, as I mentioned before, is a lot, a big amount of biomasses. Obviously, we know that in our country, in Europe, also the major part of the fish is processed before being sold to final consumer. And obviously, this generated a lot of side streams, from 20 to 80%. And obviously, it depends on the kind of fish, on the kind of process. But as you can see, you produce also a lot of unwanted catches, as I mentioned before. And all this kind of side streams, can be estimated to reach the 30–35% of global fish production. So it's mandatory to use them, and it's mandatory to pre-treat them in order to stabilize. In many cases, sorting is an avoidable step, but many research projects like EcoeFISHent are working in order to avoid this step. And now let me go through the bioactives that we can recover from this kind of food side streams. In particular, I would like to speak about proteins and peptides. Above all, what is the typical protein of this kind of biomasses is collagen. Collagen, as you know, is one of the most important proteins, above all in skin and in the bones of fishes, but also in jellyfish, in sponges, and in other marine sources. Then collagen can also sometimes be called gelatin when the structure of this native protein is partially destroyed. In this case, obviously, we are called about gelatin, and also we often called about another kind of bioactives that are called hydrolyzed collagen or gelatin peptides. So gelatin is a water-soluble biopolymer, usually, as I mentioned before, obtained by denaturation of collagen, which is present only in animals. In particular, nowadays, commercial gelatin mostly derives from bovine and porcine discards. And but gelatin demands is increasing. Is increasing because, unlike the bovine one, marine gelatin does not present problematic limitations, linked to, for example, BSE, bovine spongiform encephalopathy, foot and mouth disease, or religious constraints. So, fish gelatin is considered a valid alternative to the terrestrial ones. Nevertheless, it has to be considered that fish gelatin usually contains less quantity of typical amino acids like proline and hydroxyproline compared to mammalian gelatin, with consequences in physiochemical and functional properties, such as gel strength, viscosity, and melting point. In addition to the type of the starting material, extractive conditions can affect the properties of gelatin too. So, collagen and gelatin, I said, again would like to remind that collagen is the native protein and gelatin is the denaturated collagen status, are very, very used not only in food sectors, but also in many other sectors, like, for example, biomaterials, like packaging. And so this kind of bioactives are, quite important to be recovered. Then we have what we usually call the hydrolyzed collagen or gelatin peptides. They are something that derived from collagen and gelatin because, as shown in this part of the slide, the triple helix typical of collagen, the denaturation typical in gelatin, and then we can, hydrolyze from a chemical point of view or using enzymes, hydrolyze these proteins and obtain small molecules, small peptides. These small peptides are very useful for other kind of uses because a lot of them have some important bioactivities. For example, some of them are characterized by anti-inflammatory, antioxidant, or other important bioactivities that can be, and are also not only can, they are exploited in many sectors, like food supplement sectors I mentioned before. So this is a very precious bioactives that you can extract from fishery side streams. Another kind of bioactives are the lipid fraction, and you know that fish contains between 2 to 30% of fat. It depends on the kind of fish. So we can have very low content of fat in some fishes, but you can have a very high content of fat in other fishes that are located in muscle tissues, heads, bones, fins, tail, skin, and above all in viscera. Beyond the well-known positive effects of semi-essential fatty acids of omega-3 series, such as EPA, EPA, or DHA, I would like to remember that these compounds, as you can see in the structures, are quite unstable because they are, as you can see, there are a lot of unsaturations. And this kind of unsaturation are considered like weak points of these molecules because they can very easily be oxidized. And so when you try to recover this kind of fraction, you have to pay attention to oxidation, and you have to monitor this kind of process that could, negatively affect your final product. So what we are saying is that during your extraction, you have to be clear what you want to extract. You have to be clear that different kind of biomasses can contain different kind of bioactives. For example, proteins, for example, lipids, for example, another kind of marine source like shrimps contain a lot of chitin, another important biopolymer that could be used in many applications and in many various industrial sectors. But in all cases, you have to pay attention to the quality of this kind of bioactives. And, for example, I just mentioned oxidation for lipids, but also you have to pay attention of the concentration of some contaminants, some hazardous substances that could be concentrated during the extraction process. And so each step must be monitored in this sense. And it's important so to check both the quality and both also the purity of your compounds. These are other examples of bioactives like pigment. Astaxanthin is a typical colorant that you can find in some particular fishes like salmon on crustaceans, and minerals like calcium, phosphorus, zinc, and iron that could be used in a lot of sectors. So, just to resume, we have, to remind that you have a very perishable biomass, that stabilization is mandatory. Then you have to, extract what you want, possibly trying to use a sort of cascade process, because it's very convenient to try, to extract more than one bioactive possible in the same flow chart, but without forgetting that each step has to be monitored in terms of quality and in terms of contaminants. So for this last part of the extraction, that is the core of the process, obviously we have to follow all the principles that a good green extraction has to follow. Because, as you know, there are also a lot of traditional methods to extract this kind of bioactives, because fatty acids are not a novel ingredients, also gelatin, also peptides. But a lot of very used extraction methods are still using traditional procedures. In this kind of traditional procedures, obviously we have environmental concerns and also economical concerns. So an important topic in this kind of flow chart is to replace traditional methods with innovative ones. In particular, green extraction, and in particular, following these 6 principles that I would like to remember Professor Chemin and Professor Cravotto wrote in a lot of outstanding scientific papers. And if you are interested in this topic, I invited you in reading this kind of scientific papers in order to understand these 6 principles that is important to follow to have a real green extraction. For example, just to have, a quick overview of these principles, the first one is not to try to over-exploit natural resources, because, for example, if I try to overuse a particular kind of plant or a particular kind of animals, probably I will have a loss of biodiversity. So I have to pay attention to my biomasses that are really a sort of surplus, a sort of excedence. And for example, fishery leftover is an example. Insects are other examples, but also, substances that in a very innovative ways, some scientists are trying to extract using, for example, biotechnologies. Then the second principle is to use alternative solvents and possibly using just water or not solvent at all. Because as you can imagine, some extraction in a traditional way use what we call the traditional solvents that are very environmentally impacting and sometimes also toxic for operators. And so it is really important to replace this kind of solvents with or just water or food grade solvents, or possibly without using solvents at all, as I mentioned before. But how we can do that? We can do that in sometimes in using innovative solution, not only changing solvents, but also changing the extraction techniques. And for example, I am sure you have already seen in other lessons this kind of innovative processes like ultrasounds, microwaves, or subcritical fluids, and something like that. This is obviously of help when we decided to change solvents or when we decided not to use solvents at all. And then they are quite useful also in reduced time of extraction. And obviously they are important also to save energy at last, to save costs. Then another principle of a real green extraction procedure is that during your extraction flow chart, not only to perform a cascade flow chart, as I mentioned before, trying to extract more than one product in the same process, but also without producing real waste. Otherwise, your process will generate other wastes that then you have to dispose. So the best practice is to produce co-product and not waste, reminding that co-product is different for byproduct for waste. And this is the definition. Co-product is the material, intentional or inevitable, created during a single manufacturing process and at the same time as the main product. The main final product and co-product must always meet specification for their characteristic, quality, for example, and each may be used directly for a particular application. Then this is one of my favorite principles, because in the past, in the very a lot of times ago, I started my university careers in a chemometricians group, and I learned that chemometrics is very useful in all your experiments. And above all, it is very useful in this kind of topic, because as you can imagine, you have a lot of variables to fix and a lot of variables to optimize, because you have to improve the yield of extraction, the quality and the purity of your extracts. But at the same time, you have to save time, to save number of operation steps, to save energy, to save environmental impacts like waste that I have already mentioned. You have to pay attention to economical costs, to solvent, and so you have to consider a multivariate system. And so you can optimize a multivariate system just using multivariate techniques like chemometrics. And in this case, multivariate experimental design is one of the most convenient, methods that you can use. Finally, it's important to consider the life cycle assessment. I know that if your process is good, if your bioactive are, the best one, your steps have been optimized by multivariate design. But if at the end this kind of analysis is not performed, is not considered, you probably could have a process that is not convenient. It's not convenient from an economical and from an environmental point of view. So let me conclude this lesson speaking about these targets that I just mentioned before. And this is, what we are just, I have just explained in the previous slides, but resumed in a sort of schematic view. And in this case, I would like to show you some results that we have obtained managing this kind of biomasses. This is a scientific paper just published last year, and this is another one. The first is focused on gelatin and on hydrolyzed gelatin peptides. The second one is focused on collagen. But in both cases, we tried to use innovative techniques and possibly a sort of cascade flow chart to recover more than one products in the same process. So I would like to thank you, and please, I am able for your questions. Just before to leave the floor to my colleague Federica Turrini, who will show you other examples of case study about bioactives extracted from other kind of food side streams. Thank you.
Okay, good afternoon, everybody. Do you see my screen?
Yes.
Okay, thank you. First of all, let me briefly introduce myself. My name is Federica Turrini, and I am a researcher in food chemistry. I'm part of the food chemistry research group headed by Professor Boggia at the Department of Pharmacy of the University of Genoa. And in this second part of the lesson, we continue talking about sustainable food ingredients and nutraceutics from food side streams. Particularly, we try to answer the question how. So, how we can manage to obtain from food byproducts potentially new high-value ingredients. One of the main topics of the research activity of my research group is the valorization of agro-food waste and fishery side streams through green technologies, namely innovative extraction techniques with low environmental impact according to green chemistry and to the principle of green extraction with a view to circular economic development. These technologies allow to recover bioactive compounds with high added value, which could be formulated and then potentially exploit in different fields as new ingredients or products. An example, nutraceuticals or dietary food supplements, cosmetics, or in biomaterial applications. In this slide, I wanted to summarize some of the food matrices, both of vegetal and animal origin, which have represented or represent the side streams on which we are working, obviously in collaboration with other research groups or companies in the field, or which are supported by funded European projects. I want to mention fruit waste and in particular those resulting from the fruit juice supply chain. Moreover, the byproducts of chestnut cultivation, herbal food supplements, pigmented rice, and vegetable oils. Up to the most recent topic concerning animal products and in particular the fishery side streams, which represent the starting point of the Horizon 2020 EcoeFISHent project. There are two main case studies that I want to report on. The first concerns pomegranate fruit, which today has gained widespread popularity as a functional food and nutraceutical source due to its high content in bioactive compounds. The second one regards bud derivatives, a particular type of botanicals which are marketed in the European community as herbal-based food supplements. Let's begin talking about pomegranate fruit. And in this presentation, I'd like to answer to the questions reported in this slide, namely what is pomegranate, how is it from a botanic point of view, what's inside, so what kind of bioactive compounds or nutraceutical compounds does it contain, and at the end, why it could be an eco-sustainable solution. Pomegranate, whose scientific name is Punica granatum, is one of the oldest edible fruits quoted since the dawn of civilization and very appreciated by consumers due to its high quality attributes. It is an ancient perennial plant species of the Lythraceae family. It was mentioned in the Bible, the Quran, and in Egyptian texts. And the first pomegranate crops date back to 3000, 4000 before Christ. A plurality of symbolic meanings have been attributed to it, in example, fertility, prosperity, immortality, and it was used as a food, as an ornament, and in the folk medicine of many cultures as an healing food due to its beneficial effects on the human health. Pomegranate presents a very wide global geographical distribution, reflecting its easy adaptation to different climate conditions. Native to the Middle East and North Africa, today it is spread globally due to its high longevity, drought and salinity resistance, and resilience and adaptability to climatic changes. In particular, pomegranate is widely cultivated in 5 continents, especially in Iran, India, China, and in Mediterranean countries such as Spain, Turkey, Egypt, Morocco, and Tunisia. In Italy, this resilient and rustic crop recently has shown a growing diffusion, especially in central and southern areas, in response to increasing market demand for pomegranate, and at the same time with the aim of valorizing marginal land facing climatic changes. From a botanical point of view, the pomegranate is a non-climateric fruit and should be harvested when fully ripe, generally 5-6 months after the appearance of blossoms. During pomegranate fruit ripening, physiological, biochemical, and structural processes occur with changes in size, color, and flavor that make the fruit acceptable for human consumption. This fruit is categorized as a big berry named Balausta. Its diameter ranges from 5 to 12 centimeters, and the shape can be round, oval, and the external peels could be of variable thickness and color, which vary from yellowish green or deep pink, or red, or even black, depending on the cultivar. The different parts that make up the fruit are the coriaceous and the woody hexocarp, the mesocarp or albedo, which constitutes the spongy tissue inside the hexocarp, the endocarp, which represents the internal membranes of the fruit that surround the edible portion of the fruit, which consists of areoles containing juicy episperm and seeds containing the lipidic fraction. As regards the chemical composition of the fruit in macro and micronutrients, we can say that it is an excellent source of dietary fiber and health-promoting nutrients. It is important to highlight that the chemical composition of the fruit differs depending on the cultivar, the growing region, the maturity, the cultivation practice, the climate and storage conditions. So the reported data referring to 100 grams of edible portion of pomegranate belong to the cultivar Wonderful, which is one of the most widespread commercial pomegranate cultivars in virtue of their soft seeds and welcome organoleptic features. Fresh pomegranate contains a significant amount of micronutrients such as vitamins and minerals. In particular, vitamin C and potassium are the most abundant among vitamins and inorganic elements respectively. Its content in bioactive compounds is really interesting. Pomegranate phytocomplex is composed of more than 150 different phytochemicals, above all polyphenols, mainly responsible for its healthy properties. Polyphenols such as anthocyanins, which are the colored pigments responsible for the characteristic coloring of the fruit and the corresponding juice, and then tannins, flavonoids, phenolic acids are the major bioactive molecules present in pomegranate fruit. Therefore, this fruit is considered the source of natural multifunctional agents that exert simultaneously antioxidant, anti-inflammatory, anti-tumor, anti-diabetic, cardiovascular, and neuroprotective activities. Ellagic acid, in its free form or in the form of ellagitannins, is considered the main phenolic compounds responsible for the numerous health properties of pomegranate. and is mainly concentrated in the peels with respect to the juice. Ellagitannins are an important class of natural polyphenols classified as hydrolysable tannins, which are from a chemical point of view esters of N-hydroxydiphenolic acid and gallic acid with sugar residues, predominantly glucose. Tannins have been considered as anti-nutrient for a long time due to their poor bioavailability. However, ellagic acid released from ellagitannins in the gastrointestinal tract is partially absorbed and further metabolized by the microbiota to urolithins, which are regarded as the main active compounds with various bioactivity in vivo. As for the bioactive compounds in question, the different parts of pomegranate fruit and plants have a characteristic content of nutritional and bioactive compounds. Despite its known properties, it was for a long time a forgotten fruit and relegated to ornamental use. Many centuries later, the health-promoting properties of pomegranate have been confirmed in the scientific and medical research, and pomegranate has become a functional fruit. Today, it is considered a superfood because it is an excellent source of nutraceuticals. It is in fact considered one of the 100 richest dietary sources of polyphenols according to the Phenol Explorer database. In recent decades, pomegranate has been the subject of numerous scientific studies which have demonstrated its beneficial effects on human health by virtue of its heritage of compounds with an antioxidant activity. So, in addition to its nutritional value, ornamental and health-promoting value, it presents an high consumption and industrial value to the growing interest of consumers. In the last decades, the consumer demand for health-promoting functional foods has increased. At the same time, At the same time, eco-sustainability has become a prerequisite, influencing consumer perception of food quality. Ideally, to answer the market request, functional food should be able to provide health benefits, of course, but at the same time, it should be good, minimally processed, and possibly environmentally sustainable. The world surface dedicated to the cultivation of pomegranate is more than 300,000 hectares, and the annually world production is probably higher than 3 million tons. The main world production countries are India and Iran, where more than 75% of the world production is being produced. The juicy areas represent the most commercially exploitable part of the fruit. So, pomegranate juice is the main industrial product obtained from this fruit. In addition to the direct consumption, fresh areas marketed as ready-to-eat products and pomegranate seed oil have also recently gained an important industrial relevance. And regarding oil fraction, the major fatty acid was punicic acid, which is a polyunsaturated fatty acid with three conjugated double bonds, chemically similar to the conjugated linoleic acid. One drawback in pomegranate juice industrial production is the large amount of waste, since juice represents about only the 30% of the fresh weight, and the large quantities of byproducts are obtained from the industrial production chain of pomegranate juices. It is in fact estimated that 1 ton of fresh fruit generates about 700 kilos of byproducts. So more of the 50% of the fresh fruit weight, depending on the cultivar taken into account, are byproducts. External peels are the most abundant byproducts, representing about the 80% of all residues. Byproducts coming from pomegranate juice processing represent both a challenging, expensive, and not eco-friendly disposal problem, and a promising source of nutraceutical to exploit because, as already mentioned, the nutraceutical properties are not limited to the edible part of the fruit, but are shared by different parts, such as peels and seeds, which contain sometimes higher quantities of biologically active compounds compared to the edible portion of the fruit. For this reason, in the last decades, many researchers have focused on the valorization of pomegranate processing byproducts using innovative and low-impact extraction techniques as green alternatives to conventional extraction methods. Our research group has been dealing with the valorization of pomegranate byproducts for years in collaboration with several companies of the field. In this study, different research lines have been developed. The first study concerns recycling strategy to valorize the squeezed marks of certified pomegranate cultivars. These internal marks obtained after juice processing is represented by endocarp and seed aerials residues. And it is usually discarded or used for the oil production due to their lipophilic fraction, although it's proven to be a good source of hydrophilic compounds such as polyphenols. So in this study, a comparison was made between different green extraction methods in order to obtain the extracts that were tested in a modern food and cosmetic metrics. Particularly, the fresh squeezing marks obtained after juice processing was extracted by ultrasound, used in a pulsed modality and directly by a probe system. Water, which is obviously a basic element of both a greener and safer chemistry approach compared to other organic solvents, was employed alone as the extraction solvent. Ultrasound-assisted extraction is an example of green extraction technology widely used for the extraction of food and natural products, and able to considerably reduce the extraction times and increase the extraction yield. Using ultrasound, full extraction can be completed in minutes with high reproducibility, reducing the consumption of solvent, simplifying manipulation and workup, giving higher purity of the final product, and eliminating post-treatment. How do they work? Ultrasounds are able to mechanically break the cell walls, extracting the intracellular liquids. So the ultrasound waves act on the molecules of liquid medium, namely solvent, by alternating moments of compression and moments of rarefaction on the solvent molecules. These loops of compression and expansion cycles cause the formation of voids or high bubbles that gradually grow until implosion occurs, giving rise to the phenomenon of cavitation. To resume, the obtained extracts come from internal portions of pomegranate, so theoretically still edible, and they are organic solvent-free since only water is used to prepare them, thus making this process sustainable and environmental friendly. But so the aqueous extracts were characterized by several in vitro determination and evaluate their antioxidant properties and phenolic contents and many biological assays. Nevertheless, these aqueous extracts obviously lack long-time stability, so they should be stabilized and possibly their astringent taste improved or must. Both these requirements may be addressed by microencapsulation technology. So the microencapsulation technology applied to pomegranate extracts allow bioactive ingredients to be physically enveloped in protective wall material to increase the shelf life of the core components, protecting them from nutritional deterioration and also masking their unpleasant astringency. To stabilize their total polyphenolic content, spray drying microdispersion using pectin as polymeric matrix has been employed to formulate the water-soluble bioactive molecules, and the pectin coming from citrus peels have been chosen as carrier materials since they are another example of compounds recovered from agro-industrial waste, widely used in food production and also potentially obtainable from pomegranate peels in a closed cycle process. The obtained powders presented a good encapsulation efficiency and were able to retain the functional properties of the corresponding liquid extracts. These promising results have stimulated the preparation of a model food ready for consumption, tentatively using one of the formulations as a potential novel ingredient representing a green recycling opportunity for agro-industry. Then, in response to some real problems and always in collaboration with some companies in the sector, we explored different conditions of green extraction of the lagitannins and the lagic acid from the external byproducts of the fruit, namely the peels. Significant recoveries of the lagitannins, free ellagic acid, and radical scavenging compounds were obtained by coupling both the traditional microwave and hydrodiffusion gravity microwave assisted drying to a direct ultrasound assisted extraction, always using the food grade solvents, in particular hydroalcoholic mixtures. The study is focused on Aqua and Wonderful certified cultivars cultivated in Italy, since they are largely employed in most Western countries to produce pomegranate juices and are often grown together in order to have in the crop season an earlier and a later supply for juice manufacturing. Microwave coupled with ultrasound assisted extraction represent the best compromise to manage these byproducts in terms of extraction efficiency with respect to traditional techniques. So a new fruit-derived ingredient has been formulated with several multifaceted properties. In fact, the chain to quickly recovered bioactive compounds from these major wastes give them a specific nutritional value for their possible nutraceutical employment. The new formulation of pomegranate peel extract obtained by ultrasound assisted extraction and then titrated in both ellagic acid and punicalagin was characterized and then analyzed for potential health properties. Thanks to the active collaboration with the pharmacology research group of the Department of Pharmacy of the University of Genoa, headed by Professor Anna Pittaluga, The new pomegranate ingredient obtained has been tested in vitro and in vivo on mice in order to evaluate their potential healthy activity on neuroinflammation and on different diseases of the central nervous system. Studies are still ongoing, but the data obtained so far provides in vivo and in vitro data to support its nutraceutical properties to be exploited to improve human health and well-being in various neurological patients, providing a proof of concept to propose a potential clinical translation of this new ingredient as a botanical dietary supplement for disease-modifying pharmacological treatments. The second case study we deal with concerns bad derivatives. In recent decades, food supplements have an important impact on the consumer, showing a significant expectation for their health and well-being. They are concentrated sources of nutrients or bioactive compounds, endowed with nutritional or physiological effects, and due to their presumed health benefits, they can supplement the common diet. In particular, the interest in herbal food supplements is exponentially grown, and consequently the relative market has increased in all the world. Botanicals are became among the most popular into the food supplements category due to the general belief which natural is always better, healthier, and safer than synthetic compounds. The use of herbal food supplements as a concentrate form of vegetable extracts increased so much over the past years to count them among the relevant sources of dietetic polyphenols. But derivatives are a relatively new category of botanicals marketed as plant food supplements in the European community. They are conventionally produced by cold maceration of the fresh meristematic tissues of trees and herbaceous plants, in example buds and young sprouts, mainly spontaneously collected. These natural products are already marketed, and a long history of use as dietary supplements for human well-being and health is reported in traditional medicine. They are widely used in chemotherapy, in example, a branch of phytotherapy that exploits the properties of these plant extracts for medicinal purposes. Although both derivatives are a category of botanicals perceived as a new hand in this sector, since they are still poorly studied. But the derivatives are obtained by cold maceration in solvents, following the traditional protocol of glyceric macerates as reported in the European Pharmacopoeia, using a mixture of ethanol and glycerol as extraction solvent. The peculiarity of meristematic tissues in this particular phenological stage concerns their fragile texture and the high content of compounds which constitute the bud phytocomplex. In fact, these substances, including mainly flavonoids, enzymes, plant hormones, vitamins, amino acids, nucleic acids, are often present only in trace in the corresponding adult tissues. But the derivatives represent one of the supply chains investigated in the Finnover project, innovative strategies for development of cross-border green supply chains. Finnover project is an European Interreg Alcotra Italy-French project, which recently was concluded, whose aim is the green innovation of several agro-industrial chains. Finnover particularly provides support to the green supply chains of the cross-border territory and proposed a technical economic path aimed at the production and use of compounds of natural origin obtained from the biodiversity of the Alcotra territory and usable in the nutraceutical field, therapeutic and phytopharmaceutical field. In particular, the project develops and supports 4 green supply chains. But supply chain, which addresses the valorization of the gemotherapy field, mushrooms supply chain that supports companies aimed at cultivating saprophytic mushrooms for nutrition and therapeutic properties, lavender, which intend to highlight pharmacological, nutraceutical, and biopesticidal properties of this plant, which is a typical crop of the cross-border tradition, and at the end, microorganism, which aims to propose the new natural products that can be used in the sustainable management of crops. With regard to bud derivatives, these are the main topics addressed within the project. First problem it is accidentally confusing the raw material. Fresh buds must be collected generally from spontaneous grown in a very limited period in the late winter and or in the early spring, which corresponds to the annual germination of the plant. And during this period, plants may not show their distinctive features, and sometimes the attribution of the botanical species may be difficult for the collector. Another problem concerns the manufacturing process and the extraction protocols whose parameters, experimental parameters, are not rigorously defined, and the production rules are often vague and lacking. Then, studies have been carried out on production techniques with the aim of increasing production yield, on the valorization of the corresponding byproducts, and at the end, on the pharmacological health aspects of the mechanism of action of these products. A protocol has been developed to evaluate the authenticity of these products, which, as I mentioned previously, derive from vegetable raw materials obtained from spontaneous harvesting, providing companies that operate seriously in this sector with a defense tool on the market from similar low-quality products or even non-authentic products. In this regard, it is good to remember that in addition to the wrong attribution of the botanical species, which is difficult if not carried out by an expert collector, can be associated with an incorrect identification of the phenological bud stage which lasts only a few days. The evaluation of the authenticity of the bud extracts, both to verify the correctness of the botanical species and the correct phenological stage, was carried out through rapid screen to be transferred directly to the company during the production phase, with non-specific untargeted spectroscopic fingerprint combined with chemometric techniques and consequent confirmation using targeted chromatographic fingerprint. So several data has been published, as reported in the slide, as well as in the project feasibility plan. The polyphenols content of bud derivatives is strongly influenced by the manufacturing processes, whose parameters as already mentioned, are often not strictly defined, and thus they affect their final composition. This research aimed to answer to the growing demand for efficient quality control in the bud derivatives field, to guarantee the proper attribution of the botanical source and their content. An innovative extraction protocol with low environmental impact was therefore tested and optimized according to the principle of green chemistry and green extraction through the use of ultrasound as a potential alternative to traditional maceration, with notable saving in terms of time, minutes instead of months, with the same field, chemical and pharmacological identity of the finished products, thus obtaining a substantially equivalent product, but with lower environmental impact and greater economic field. In this research, two different manufacturing processes using two different protocols and many species have been considered as a case study. An untargeted spectroscopic fingerprint of the extract coupled to chemometrics provide to be a useful tool to identify these botanicals. And the targeted phytochemical fingerprint by HPLC provides the screening of the main bud derivatives, polyphenolic classes, highlighting a high variability depending on both production method and protocol used. In this research, an alternative method to produce ribes nigrum bud derivatives is presented. Particularly, pulse ultrasound assisted extraction using a food-grade solvent has been employed and compared to the conventional extraction method. Also in this case, untargeted polyphenolic fingerprint, so fluorescence UV visible FTIR coupled with chemometrics are employed to quickly screen the best extraction condition evaluated by the design of experiment, and then the polyphenolic fraction of the optimized extract was quantified by targeted chromatographic analysis, and its anti-radical activity was determined. Another topic regards the valorization of byproducts. But derivatives are quite expensive compared to other botanicals, since the phenological stage of buds or young sprouts necessary to obtain them is extremely limited in the time. So their collection is limiting over the time. Consequently, the valorization of their byproducts could have a significant economic impact for the producer, and it could be an important innovation in this field. In this industrial production, starting from buds, we obtained the commercial product, which is the glyceric macerate, after many steps, so maceration, filtration, and decanting steps. And together with this, after filtration, remain the bud waste. So, using ultrasound-assisted extraction, we demonstrated that this waste is still rich in bioactive compounds to exploit in different fields. This research describes a novel tool to enable manufacturers of bud extract to evaluate the sustainable waste management option in order to increase their productivity. Nevertheless, the same strategy could be analogously applied also for other herbal preparation, becoming an example of modus operandi in a green economy strategy. Particularly, Castanea sativa has been used as case study, since this species is one of the most commonly used herbal medicines for its well-known health-promoting properties. and the valorization of bad marks remaining after the production of the glyceric macerate could have significant economic impact for the commercial producers, representing an important innovation in this field. These byproducts prove to be still rich in bioactive compounds, and an alternative to their incineration or composting has been presented in order to obtain high added value products, particularly using the same solvent of the glyceric macerate, so the commercial product. We have allowed to rapidly obtain an extract with promising content in secondary metabolites. Moving on to another supply chain of the project, namely lavender, was explored the innovative use of ultrasound for the recovery of waste from the production of the lavender essential oil. In particular, following the conventional distillation of the essential oil, next to the liquid byproducts such as percolate and hydrolate, which have also been characterized with a view to their valorization, remain a solid waste. And the remaining solid waste, characterized by the residues of the flowering tops, has been the substrate of subsequent extractions, obtaining extracts that proved to be rich in bioactive compounds, mainly polyphenols and flavonoids, and usable as repellents for aphids or aimed at the production of the cultivated Pleurotus striatus mushroom. I want to conclude this presentation by reporting another food matrix, which is represented by an aromatic Italian variety of colored rice, which grows spontaneously and is called violet nori. The peculiarity of this rice variety is the purple color of all the parts of plants, so not just the caryopsis, but also leaves are purple, and they are rich in polyphenolic compounds, especially anthocyanins. First, in this work, we optimized the extraction condition to obtain anthocyanins and other antioxidant compounds from this matrix. Make also a comparison with traditional extraction techniques. We made a comparison between these varieties of violet nori and other commercial cultivars of black rice, highlighting that this variety was very interesting and a very interesting dietetic source of valuable anthocyanins and other antioxidant compounds. In a second step, we made a comparison between the polyphenols compounds of the extracts obtained from the rice, from the corresponding flowers, and from the corresponding leaves, which showed higher content in these bioactive compounds, especially making leaves very interesting for the extraction of these compounds, also on an industrial scale. The analysis of violet nori flower largely confirmed the results obtained for the caryopsis, and so flour is generally obtained from grains which were discarded for their sides or their blemishes. In fact, flour largely maintains the treasure of antioxidant molecules, and this result is particularly important since these byproducts of rice processing could be employed not just for the extraction of valuable antioxidant, but also as an ingredient for the production of valuable food products, for example, for celiac disease. My presentation is finished, so I thank you all for your attention, and I leave the floor to all of you if you have some questions. Thank you.